So this is the first capsule of my first semester series of everything I learned, and basically recapping really quickly and short and concise videos of absolutely everything that I learned. I'll try to cover absolutely everything. But the whole point of this is for anybody that is watching, if you're watching this, to know what is being taught in CJEP. I went to John Abbott College, so this is the first semester in John Abbott College. I had 4 science courses. Calculus, mechanics, general chemistry, and programming. And this is for Calculus 1, Unit 1. We had 3 units in calculus, and each unit had 2 quizzes and 1 test. So this is really for me to keep everything that I learned, because I spent so much time learning it. I don't want to forget it. I mean, I will forget it, and I know that I will, unfortunately, but to keep something to record it so that it's not completely to a waste, and I can maybe come back to my whatever knowledge I had at this moment. I finished all the finals, so everything's still fresh in my mind. We're just gonna jump in right away. It's gonna be concise and fast. So first, not chemistry, calculus, we start with some review from high school. And the most basic or fundamental stuff you're going to need is factoring. So in factoring, there is the basic factoring where you factor out, this is the GCF factoring. You just take out the greatest common factor. Honestly, if you are good with if you still remember all your factorings in high school, it should be really easy. This is the difference of cubes. Squares, because we have both cubes and squares. And when it comes to difference of squares, you also have to be careful with x to the 4 minus 1, especially because you kind of forget that reduces to, well, that factors to x to the 2 plus 1, and here it still factors x plus 1, x minus 1, and x to the 2 plus 1. So just remember to fully factor out, because that's something I kind of forgot. And here's the sum of cubes and squares. Sorry, it works for both sum and the differences. I didn't do it really a lot in high school, but basically positive, negative stays, and there's no exponent for the first term. Second term, squared for each of them times AB, and then squared for the last one, whereas it is minus for a plus sign and plus for a minus sign originally. So if it was a difference, put a plus here. If it was a sum, it put a negative here. And now we have the PSP factoring, the most classical, basic, your best friend factoring. PSP stands for, well, at least for me, products and sum. Product of 8 times 1 is 8, it's not 1, is 8. And the sum is whatever that's in the middle, so it's 6. So we have to have 2 common numbers here that match up to become a product and become a sum. I hope this is really, really easy for you. In this case, it is 4 times 2 and 4 plus 2. So what we're going to do, if it's a monic means that the first term that has a square, x square usually, is factor 1. So this is x, 1, x to 2. So this is a monic, meaning well, you don't have to write down again that it is 4x plus 2x plus 8. You can just directly jump into x plus 4, and x plus 2 is the right answer. And if there was something else like 3 here, although that's not true, let's say that's an example, then you have to include the 3, and you don't just write the factor form right away. You have to include the plus 4 plus 2. Again, I'm just making this up. This does not factor. This is a wrong example. But if there wasn't 3 or any, even the minus sign, that's the tricky part. Even if it's a minus sign, it is not a monic. Even if there's a minus sign, that is not a monic expression. So you have to, in that case, include minus x to 2. And again, these guys will have x with them. So plus 4x plus 2x plus 8. And then you'll have to factor these out by grouping. But in this case, it was a monic, so it will be plus 4x plus 2. That's a 2. Yeah, again, these should be really, really simple, and I'll come back to the limits. But so grouping is the second most, well, maybe not second most, but Also really important technique, basically grouping them like the name says, and factor out the biggest, again, like the GCF. And you can here factor out -4, and you'll see that it becomes, there is two common factors, x plus 3, it groups up, x to 2 minus 4 groups up. So if you distribute this, if you distribute that, it should give, or it does give, the expression of multiplying the x to the 3, which is common, and x to 2 minus 4. And you can see that x to 2 minus 4 also factors even further. So this one becomes, oh my god, x plus 2, and that's the final answer. So the whole point of factoring and everything is for you to go touch some limits. And limits is like the first ever concept of calculus, and some people find it hard. I won't say that it is hard, and I don't want to say anything is hard, but limits is basically a very, very easy concept, and it is hard if you are not able to grasp it the first time. But basically think of a function that has a hole or has an error. It's like a function that has a bug, and that's not really the true definition, but if let's say we go with a very simple removable discontinuity limit. Removable discontinuity, the word discontinuity sounds really fancy, but it really just means that there is a disconnection, that there is a space that has nothing, that the function does not exist. DNE is another term that you're going to use a lot in limits. So basically limit means when you approach the value of, let's say 2, that the function does not exist, but we want to know what that value was if it did exist. That's the whole concept of limit. That's that one sentence just describes the entire limits chapter. What would it have been if it did exist in a function where some value did not exist? And what does it mean when it does not exist? How is it possible that something does not exist? It is really possible, because if you divide something by 0, well, it is undefined, whereas the whole function itself should exist, like this one. Everything exists, it's except for this one value where x is equal to 2. So what's happening is that when it approaches 2, it exists. So throughout 2.000001, or in this case 1.999999 exists, but exactly at 2 it does not exist, and we want to know what that value is. That's all. That's how, it's as simple as that. And when it comes to piecewise functions, it's the same principle, but there are other types of discontinuities. This is a removable, because we can, it's as if I removed this dot right here, right? If I remove it, it's gone. Yeah, that's the removable discontinuity. And the limit of the removable discontinuity exists from both sides. From both sides means from the left, approaching from the left, and approaching from the right, they have the same limit. Because if I approach from the right, from 2.0001 approaching to 2, from 1.9999 approaching to 2, they have the same y value, because they were approaching the same dot. But not in here. If you're approaching 3 from the left and approaching from 3 from the right, it does not have the same value if it ever did exist. Here it does not exist, the value does not exist. Here the value does exist, but we do not care if it exists or not when we're looking at limits. It could exist. It could have been a function like this, where it's a 2 here, and it totally exists. The value literally exists. But we could still look at the limit. What is the limit here? The limit has nothing to do with if it exists or not. We're only looking at what it is approaching. So if it was, again, a function that... Oh my god, why is this not erasing? Sorry. If there's a function that exists, and it could have been a linear, like a really normal linear, and they will ask you what is the limit. At 2, let's say if this was a normal linear, it will exist, the function and the limit will be the same. Here, the limit does not exist, because the limit, as you approach from the left side, which is usually with the sign negative, and the limit from the right side, which is with the positive, is not the same. This here, let's say it's approaching 2, and this here is obviously approaching 0. So from the left is 2, from the right is 0, then the limit does not exist. DNE. And what is so important about this? What is the takeaway? There are going to be questions like what is the limit at x equals some value? What is the type of discontinuity at x equals to some value? There's removable, there's jump, and there's the infinite, a bit like this one, the infinite discontinuity, meaning that when it approaches 0, let's say, when the x value approaches 0, what is the limit? Well, it is infinite. So it depends on how your professor will want you to answer, but it could be either D and E, or some teachers say negative infinity, because when you approach 0, well, y value will approach negative infinity. Technically, you could say D and E, you could say undefined. It depends on what your professor wants you to say, but basically there is no value you can give here. So that's pretty much it for limits, and there are many examples that you'll have to know. But before we jump into examples of limits, I just want to cover another review topic. And again, I kind of didn't mention it properly, but the whole point of factoring that I just showed right here, many factorings that we did, all of that, we needed those to find out what was this value right here that was missing. So by factoring and canceling out, because when you factor, it becomes few terms that look quite simple. And in most of the cases, well, not most, all of the cases that they're going to give you, if it is a factoring question for limits, whatever that's on the top and the bottom, some of them should match. So it could have been like a +1 here and completely different stuff here. But then what happens is that you can cancel these out, right? What happens is by canceling out, you're basically filling in these gaps. So the question of limit is to fill in the gap of a function that does not exist right there at that x value, to find out what it was approaching, or what it would have been if it did exist. And that is why you need to know your factoring, and that is how factoring will help you find the limit. And now we're gonna jump into some trig review. So this is the most fundamental trig. First of all, you should know your trig circle. I won't draw out everything, but the most basic ones: pi on 6, pi on 4, and pi on 3. Here it should be, you should really memorize your trig values, and I mean for the entire trig circle. One of my trick is to know that it's actually really easy to memorize the trig circle. I don't think I'll go into too much detail, but for whatever x and y value, remember these two guys. And when, obviously, by drawing it out, you can see that this is longer, and this is shorter, and this is shorter, and this is longer. Which one's longer? This one's longer. This one's shorter. So then this is longer. The x value is √3/2, and the y is half. You can also think of it as like, that's like the half of the circle, like, I mean, half of 1. This is 1, and this is -1. Whereas here will be the taller one. The taller one will be, obviously, √3/2. So that's the y value. X value is the shorter one, so it's half. And yep, that is correct, because that's what the circle says. And for whatever other, or the rest of circle, you could just look at it like they're the symmetry or the opposite sign, whichever you want to think about it. These will go 6, pi on 6, well, I like to think of it as each group. This is pi on 6, so when you divide, because here is pi, when you divide from here all the way here into 6 parts, each part will be a 6. So 1, 2, 3, 4, 5, 6. So each of these from here to here to here is a 6. A 6, a 2 on 6, 3 on 6, and then 4 on 6, 5 on 6, and 6 on 6, which gives pi. But each of the whatever fraction I said could be simplified to like pi on 3, or here it could be 2 pi on 3, because that was, again, 1 on 6, 2 on 6, 3 on 6, which is a half, so that's a pi on 2. And 4 on 6 can be reduced to 2 pi over 3, and that's how the trig circle is drawn. And then there's the pi on 4. Well, you can keep going, actually. This is 6 on 6, 7, pi on 6. And then here, my drawing's not that perfect, but so that's 7, that's 8, that's 9, that's 10, that's 11, and then that's 12. Basically cut it into, cut the circle into 12 pieces. But 12 pi on 6 is basically 2 pi on 6, so, 2 pi. So then that will work for this circle. And then there's the pi over 4 here, which is even easier. Think of it as a quarter every time. So pi over 4, 2 pi over 4, 3 pi over 4, 4 pi, no, 2 pi, sorry, 4 pi over 4. And then the pi over 3 is from here to here is pi over 3. From here to here is pi over 3 again. From here to here is another pi over 3. So then there'll be 3 pi over 3. And you keep going. It's the same principle from here to here. And then from here to here. And then from here to here. Those are the third. Again, it's just really lifesaver, actually crucial for you to memorize the trig circle. If you don't memorize the trig circle for calculus, you're in trouble, I think. It's not that easy without memorizing it, but again, it's not too hard to memorize. So this is another expression that you totally need. Sine to the 2 theta, or x, plus cos to the 2 theta, or x. The theta is just a variable, could have been x, is equal to 1. And what you can do with this is by actually dividing everything by something. It could have been cos of theta. So if you divide everything by cos of theta, what happens here? What happens here is tan to the theta plus 1, because it's cos to the 2 theta divided by cos to the 2 theta will be 1. And here, 1 over cos is secant. So 1 over cos to the 2 theta, well, theta, x, whatever variable, is going to be secant to the 2x, or theta. I should write theta. So this is going to be secant to the 2 theta. And you can do the same thing, again, from here, from there. You can do the same thing, but for dividing it by sine. I don't want you to get confused, although it might be already too confusing. So if you divide everything by divided by sine to the 2 theta, what's going to happen here is 1 plus, now it's going to be cotangent to the theta, because if you divide cos by sine, that's a cotangent, and if it's a square, then it's just a square root of cotangent. And here, 1 divided by sine is cosecant, and if it's a 1 divided by sine theta, it will be cosecant theta. If it's a 1 divided by sine to the square, it's cosecant to the square, so it's a cosecant square of theta. And these expressions are very handy, crucial, totally crucial actually, because they will give you, the calculus exams will give you questions that you have to come up with simplification. So if they give you a cotangent to the 2 and you don't know how to simplify it by other means, then you know that 1 plus cotangent to the 2 is equal to cosecant to the square. Or actually, that's the opposite. Let's say you know what is a cosecant of square, but you don't know what is a cotangent of square. Either way, you have this relationship, and by manipulating it algebraically, same goes for this one. Let's say you know some facts about tangent to the 2 square, tangent square theta, but you don't know anything about secant square theta. Then you can use this expression to, by doing algebra, find out whatever you need to find out. So that's the trig review. So remember all your points, x, y's, your circle, factoring. That's basically all for review. And by limits, we already talked about it, but there are a few notations that we kind of have to know. Totally have to know. Limit as x approaches something. It could have been an a. This is a lim. Of f of x of the function is equal to L. That's how we write down the limit. The showing what this is the notation of the limit. And again, like I said, there is the limit as x approaches a. A is any number. It could have been 2. Let's use 2, because sometimes it's confusing with letters. Limit as x approaches 2 from the positive side, and as x approaches 2 from the negative side. That is like when we talked about from the negative from the left, from the positive side from the right, and that's the same here. And it could apply to basically anything. And we should write f of x, but again, f of x can be anything. It could have been, I'm just gonna make something up. It could have been x plus 2 and x minus 1 over x minus 1. This is a really obvious case where you can cancel things out. But this graph basically looks like a line that goes up that has an empty hole at 1. And I said 2 here, but let's change that to 1. If we're asked the limit as x approaches 1 from the positive and from the negative side, you can see that it's the same because from the right and the left, they're approaching the same value. But then if you didn't look for the limit and you looked for the function, the f of 1, you would have to answer D and E because it does not exist there. It is an empty hole, so it does not exist. But we can look for whatever that value was supposed to be if it did exist. That's the purpose of limits. And by calculating limits, what are we doing? I'm telling you, forget about limit or anything, or confusing your brain by the word limit or definition or the D&E or anything discontinuity. Just forget that. And basically, limit is canceling things out. Canceling things out, simplifying things. Like, technically, even if I didn't look for limits or whatever your prof is telling you to find, if I show you this function, like, are you not eager to cancel this out? I think you would be. Let's say I had a times b divided by a. Like, that's just b. Why? Because that cancels out. Like, if this is your mathematic intuition, then you're totally good to go because that's the whole point of limit, the whole chapter of limit. You want to cancel things out, and you'd realize that when you do cancel that out, that all the problems are made so perfectly that it's actually the value where the 1, the positive 1, is turned into a negative 1. Because if by plugging in 1 here, if you plugged in 1 here, what's going to happen? 1 minus 1. And here it's going to be a 1 minus 1. And by doing 1 minus 1, obviously that gives 0. And by giving 0, this whole function, when you solve it, and by plugging in 1 in your x values, they're going to give you 0 on 0. They're going to give you a 0 on 0. And that is undefined. And anything that's divided by 0, first of all, does not exist. And the top does not really matter. We're going to talk about it soon. But basically, if the bottom is 0, the function does not exist. Dividing anything by 0 does not exist. So that's why we need to use these factoring to find out what was in that empty hole. Now, it was a little bit of a mess, but I promise it will be more organized as the video goes, and we're gonna go through the ideas of limits. Whatever I just said right now was kind of like a brief overview of the limits. Now, if we jump into proper examples, limit approaches 1 of x of 2 plus x minus 2 over x minus 1. The whole point of the limit is to find out the limit as x approaches 1 when the x is approaching 1. The function could exist, but we do not care if it exists or not. However, the first thing you should do all the time, is to first plug it in. Just plug in normally. By plugging in, we have 1 plus 1 minus 2 over 1 minus 1, and that's going to give automatically 0 and 0. And you should always do, like, a side note here, ds, direct substitution, and that gives a type 0 and 0. There's a few types it could end up being by normally plugging things in. You should totally normally plug things in, because sometimes it's a bit of a silly question if it is, but the function does exist, and you're looking for the limit, which is equal to the defined y value there. If this was the function, they're looking for the limit at 2. The limit at 2 and the function of 2 is the same. So if you plug it in, you will directly get the answer. Let's say you plug in, and the function actually looks like this. Whatever you get for the limit, let's say if it was a 2, is actually the same function value. And if you're lucky, and if the teacher was being silly and did give you that kind of question, you don't need to do any of the factoring or simplifying or any of that technique. You just need to plug in. So plugging in is definitely a juice. And not only that you can save your time, By factoring, there's two types of answer that you're going to get. It's either a 0 on 0, remember all the time, or C on 0. By C, I mean constant. Any constant. It could be 3 on 0, it could be 2 on 0, 1 on 0, 32 on 0. Anything that is on top of 0, it's very unique, and we're going to look at what these are. I'll actually spoil it to you. It's an infinite discontinuity. It could be a plus or minus infinite discontinuity. We're going to talk about that shortly, but the whole point of plugging in is to find what type of limit this is going to be. And at 0 on 0, there are a few types, a few patterns. There's a few cases. It could end up looking removable, and it could end up looking, I actually don't know what else than removable. Yeah. Well, you don't really need to know what it will look like. You just need to operate. You just need to function. That's the life of a student usually. X to the 2 plus x minus 2. Well, you can use the PSP factoring and that factor out to x minus 1 over minus 1. And by doing this, we can cancel it out. And then what we get is x plus 2. And now we can just plug it in. And you have to always write the limit, x plus 1 limit, x plus 1. And you just plug it in. And finally, when you do plug it in, you no longer need to write the limit as x approaches something. Then the answer is 3. So what it looks like for this case, well, this was a linear. Again, you don't have to know that it's a linear. But the case here, in graphically, you can always use whatever. I like to use this MOS. But whatever from graphing website, you can just type in the whole expression right here to see what it looked like, and it will give you the function. And when you approach that value, you'll see that probably if it is a removal, then there's like a gap in between. So that continues for many for a lot of, so this canceling out is the major type. Another type is the square root, the roots. So limit of approach 3 on 2x plus 3 minus 3. I'm going over the most common, well, the three or four types of limit questions. This is another 0 on 0 if you plug it in. And for here, we do not just factor. We do factor. That is part of it. Like this one here, you can factor. But we first have to do something called the rationalization. And rationalization basically comes from this idea, the difference of squares, by applying the difference of squares to the roots. So what happens if you do the formula on these roots? It becomes rationalized. Instead of a minus, like we had a minus right here, instead of minus, we're going to use a plus. And magic happens. No, it's not magic, I'm joking. Here we can simplify this to x to 2 minus 9. This could be simplified further. We're gonna do that just later. And whatever you do to the top, always do to the bottom. Whatever you do to the top, you do to the bottom. I always tell this to whoever I am teaching, whether that is my younger sibling or any other students. Whatever you do to the top, you do to the bottom. The same thing, you do a plus here, and you break it down, multiplying each other. This one will give, well, this follows the difference of squares rule, minus 9, and that is because a to the 2 minus b to the 2 equals to a plus b times a minus b, and well, you know that a and b is each the root of this, and if you can do it, if you do the opposite, if you do the contrary, a plus b, a minus b multiplied will give a squared. So this is a squared, and this is b, so b squared, which gives that. This squared is just taking away the root, and that's what we want. We don't want the root because we want things to look nicer, and I'll tell you, calculus looks really nice because everything just cleans up. And you can see also that 3 and 9 can simplify even further, and that's the whole point of rationalization. After you rationalize, there's always one or more constants usually that will simplify even further. But let's just move on here. It's going to be x plus 3 to x plus 3 plus 3. So the bottom, there is no problem in here. You don't need to simplify or anything. There's nothing to simplify. It's just tagging along. Oh, and I forgot to write my limit equals 2 every time, but you should. And then you simplify everything, you cancel out stuff. You can already kind of see it, but this becomes x to x minus 6 over 3x minus 3, x plus 3, and then root 2x plus 3 plus 3. And here you can even simplify it further. This one will become 2 times x minus 3. And x minus 3, like I said before, cancels out. Stuff will always cancel out. And by doing the canceling out, you can actually also realize that it's x approaches 3 and x minus 3 that cancel out. It's not a coincidence. It will always be the case, and that's the whole point of canceling things out, because then by canceling out, you're basically filling in that hole that was missing stuff, right? And by plugging it in after simplifying, this will give 1 over 54. You can try that. That's a rationalization method. We also can do rationalization upside down, kind of. Same concept. In this case, let's say it's a limit as x approach minus 1. Oh my god, that's too tiny. Limit as x approach minus 1. In this case, we're just going to do the same rationalization on top and bottom, but like this instead. So you can see here that this we kept the same because that's what was here, and whatever the sign that was in the middle, we'll change it. So if it was a plus originally, we'll change them to negative. And if it was a negative originally, if it was a negative here, then we'll change these two to be positive. And you will just do the same thing, just multiply things out and they will cancel out. I could do it here, but 3x plus. Yeah, so this will become, I don't need the green one. Approaches minus 1 of 3x minus 1 minus 10 minus 6x over, well, so the top stay the same and bottom will multiply the common, so the a's and the b's will become a square. 3x minus 1 is going to become a square, and there's always a minus sign, and the b, which is these guys, will become no more roots, because by squaring it there's no more roots. And you can keep solving, cancel things out, and well, here you can see that 3x minus 1 to the 2. Distribute this, and it will simplify. So 10 over 9x minus 1. By distributing this, and by so by distributing this and by adding it to the 3x minus 1, you can simplify further down, and it becomes a 9 times x minus 1, whereas the top, sorry, my x minus 1, x plus 1. Oh, it's because I forgot this one, sorry. Forgot the x plus 1 all the time. So there's a x plus 1, and there's a x plus 1 here, because when you distribute 2 minus 10 minus 6x and you add it with 3x minus 1, that will give you a 9. This was going to give you 9x to 2 minus 1. And by simplifying the difference of square here, it will become x minus 1, x plus 1, and x plus 1s, they will cancel out. And by canceling out, you will plug in, this is x, you'll plug in your minus 1, and you're going to get the answer, which is 4/9. Complex functions, it's basically where the fractions are really complicated. There could be a over b divided by c over d, which simplifies to a over b times d over c. And it could be a over b divided by c, and that's a over b times 1 over c. And these are some rules, I should say, I don't know, that you should remember, because it always comes in handy. And if you mix up when to switch upside down or when to turn it into a multiplication, if you mixed up and did times 1 over c over 1 instead, that would give you a completely different answer. So always remember, if it's divided by something, it's always multiply by 1 over that same something. It will never be a over b times c. This one, that's wrong, because c is not a fraction, it's a constant, so it has to be a over b times 1 over c. If it is just times c, you're telling me that a over b divided by c is the same thing as a over b multiplied by c, and that's not true. So by applying that, you can do limit questions such as x approaching 2, 3x minus x plus 10 over 2 divided by 2 over x minus x over 2. And you can type this into whatever software or website that will show you the function. But by, first of all, you have to make sure that it's brackets, and then by distributing the minus signs, or you also don't want to forget about the distribution, or you can either do the distributions after you break it down. So in this case, I usually like to separate it into 2 fractions, like two expressions instead of one huge one that has a top and a bottom. But in this case here, we can actually do 6x minus x minus 10 over 2. So what I did here is just multiply 2 with this 3 here, so that they have a common denominator. And on the bottom, we have, well, the same thing, but 4 minus x to 2 over 2x. Just need to find a common denominator between 2 and x. This should be a really basic high school math. And 4 minus x to 2 comes from, again, denominator, whatever you do to the bottom, you do to the top. And it will become 4 minus x to 2. And this actually transforms to a much nicer expression, 4 minus x to 2 minus 2x. And it's actually easier to work from there because the expression, oh no, sorry, I literally did the mistake told not to do. So when you flip it upside down is used when you are turning a division into a multiplication. So whatever that was on top and bottom will become bottom and top switched places when it's turned into a multiplication instead of division. That is a commonality for all of fractional divisions and multiplications. And by doing this, you can, oh, I forgot my divide by 2. By doing this, you can just simplify by simplifying that one, simplifying this one. And what happens here is x minus 2, 5, take out the 5, 2x remains. And 2 minus x, 2 plus x, because 4 minus x to x square is a difference of difference of square. That becomes 2x, 2 minus x, and 2 plus x. And by simplification, you can always scratch out things. And this is a really unique, my favorite actually, pattern, where there's a x minus 2 and a 2 minus x, which is the opposite sort of subtraction. What you have to do is, you can cancel it out but don't forget to put a minus sign in front. Just one. Because x minus 2 is actually the same thing as minus 2 minus x. By distributing it, you will see that it turns into a minus 2 plus x, which is the same thing as x minus 2. That's like one of my favorite tricks. Well, not a trick, but it's a fact. And I again forgot to write my limit equals 2. And I highly suggest you to not, because teachers will take off points. So this one becomes 5 times 2 times 2. And you can realize again that when it was approaching 2, we canceled out stuff that was about minus 2, x minus 2. Because by plugging in 2 here, what's going to happen? 2 minus 2 will become 0. And 2 minus 2 here will also become 0. Whatever multiplies by 0 will become 0 on 0, right? And that's what we want to avoid. That's why we want to fill in that whatever gap. By filling in that gap when it's 2 is done by, well, the English is not working, but whatever you fill in is whatever you're canceling out most of the time. And here it's approaching 2, then you're canceling out x minus 2. Like that, whatever the 0 on 0, whatever was causing the 0 on 0 will be canceled out, and there's no more 0 on 0, and you'll get a value by factoring it out. Oh, I wrote x plus 2. And that's it. You plug it in, because after you cancel it out, there's no more 0 on 0. You will not see a 0 on 0 after you factor out and cancel things out. And because you want to cancel things out, that's why you need your factoring abilities. So that gives you. So those are the three main most used, actually the only ones, at least at Jack, that are taught. 3 techniques. The first one being factoring and canceling out. The second one being the rationalization using the roots and the difference of square formula, and the last one being the fraction, so just turning fraction into a different format and then canceling out. And another one is a theorem that you have to just accept. Sine of x. When at limit x approaches 0, sine x over x is 1. And lots of teachers will tell you to just remember that. Or x over sine of x is 1. Again, as limit as x approaches 0. This is for type 0 on 0. Actually, if you plug it in, it will give 0 on 0. But there actually is a reason to it, and there is a reason that my prof taught me. If you draw out the sine function... Oh no, that's not a really nice drawing. Oh no. If you draw out the sine function, you will see that it actually continues here. At 0, the slope is 1. The slope is 1. And why do we care about that? Is because if you can see here, we're doing like a y over x situation, because y is a function sine of x, and the x, well, obviously is the x. And when we do y over x, if you remember, delta y over delta x is equals to a, or the slope. Some people use m, is equal to the slope. And when x approaches 0, this delta becomes extremely small. This delta x or the delta y, the delta is basically the difference, right? If you had a graph from here to here, the delta y is that and delta x is that. And whatever your 2 points will connect, well, the slope here is the value of delta y over delta x. So basically this one divided by that one. But if this becomes extremely small, that's the theorem of derivatives. You don't need to be surprised or attacked or shocked by the names. The names are just fancy for no reason, I'd say. Is when this distance here becomes extremely tiny, that approaches 0, and technically 0 because it is just so tiny. It's basically a dot, like 2 dots that were separated from each other, like here, is now like super close to each other, and the deltas, you can't even see it. And that is the theorem of x approaching 0. Sine of x over x will just be the slope at when sine of x is 0. And what is the slope? It is 1. Because here, the slope here is 1. And why is that slope 1? I think you're going too deep if you want to know that. You could be a nerdy person and go search up the demonstration of why it is 0 here, but it is not in the course, and I don't think it's in any kind of calculus course to have to know that. So doing some trig expression for, again, reducing stuff. You have to reduce stuff and simplify stuff. This one, cotangent. Approaches 0, I forgot my 0. Cotangent is cos of x over sine of x. And like I said, x and sine of x simplifies out. It becomes limit as x approaches 0 of cos of x. And you just need to plug it in. And when you plug that in, it will exist. When you plug it in here, it did not exist because you're doing 0 on top multiplied by another 0 here. Because sine of 0, sine when the angle is 0, is 0. The height is 0. The y value, the height is 0. So there is no limit if you just plug it in normally. The function does not exist at x cotangent of x. Because if you plug in 0, it will give 0 on 0 undeterminate form. But by looking for the limit, that's a different concept because you can cancel things out. And that is nice because there's x on sine of x or sine of x on x. And cos of 0 does exist. That is equal to 1. Again, trig circle. That's why you need to know it handy. I memorized my trig circle and it totally went well in my ear. So that is pretty much it. Other simplification exists. Note that x over x square over a sine square over x and x square also cancels out to 1 because that's basically saying sine of x times sine of x divided by x times x, and that cancels out to 1. So 1 on 1 is always 1. The answer is always 1. And they can mix. I don't think they will mix actually. They will not mix in trigs with other things like rationalization. They will not mix sine and trigs with roots most of the time. I've never seen that in my case in my class. So they will be independent. If it's a trig question, it's gonna be staying trig. If it's a fraction, it will stay fraction. Another, the second concept, the second type of limit. Well, right now we only looked at 0 and 0. Throughout this video, we only look at 0, 0. We're going to finally look at what is c on 0, constant on 0. So that is when, let's say there's a 4 over 0.1, 4 over 0.0000001, or 4 over 0.000000001, and whatever that is on the top does not matter. It could have been 0, it could have been 4, it could have been 10, 20. But if you realize, if you type it into your calculator, this will give like a 40. This will give 400. 4, 1, 2, 3, 4. I think. And this will give even more zeros. I am not precise, but it just gives more zeros as the value at the bottom becomes smaller and smaller. Because we're dividing something. That's an apple. By a very, 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 very small number. So if you divide this into a very, very small, by a very small number, you will get a very, very big number. Yeah. So c over 0 is going to be plus or minus infinity. And this plus or minus is all you care about. If you see a constant over 0 by plugging in, again, this constant of 0, how you find it, is the very, very first thing I said to do. Direct substitution. If there's like a expression that I'm not sure, I'm just making things up. And when you plug in, it will give you, plugging in will give you, let's say that gave a 5 over 0, which is not possible, but let's say that gives you a constant over 0. What you are interested in is not factoring. It is not canceling out. Canceling out and simplifying things are for 0 on 0. 0 on 0, you simplify or factor. But c on 0, you could simplify, but the whole point is not to cancel things out and make it smaller. It could be in the process, but the most important goal of when you see a c on 0 is to find out if it's plus or minus, if it is negative or positive. If the limit is approaching positive infinity or if it's approaching negative infinity. And usually those are asymptotes. It could be asymptotes, but it could even be, if it's exponent function, it's not an asymptote, but it's just going forever infinity positive. Or if it's a logarithmic, it could be going infinity negative. But most of the cases, you do not really need to know the graph. I did not know what the graph looked like for any of the questions I do, because you just really don't need it. You just need to use your tools to find out the answer. Let's say we do an example. By plugging 4 in, you will get a -8 on 0. And you do not try to cancel things out somewhere. No, that's not the goal. That does not help, actually. What you have to do, what you really care about is the bottom, is the denominator. And that is because you want to know if it gives what kind of 0. Does it give a positive kind of 0 or a negative kind of 0? What does that mean? Let's say I have, first of all, if I plug this in, will be just the denominator. The denominator is 8 minus 8, right? And that 8 minus 8 is what gives me the 0 over here. What we care about is if that 0 is coming from the positive side or the negative side. And that's something I kind of struggled about if you were not taught perfectly. Let's say this is 8. That's 7. That's 9. Approaching 8 from the right, approaching 8 from the left. What does that mean? It's if it was approaching from the right, then it would be 8.0001. If it's from the left, it would be 7.9999. And by plugging in either this or this, it will give different infinity result. If it was a 7.9999 that we plugged in here, if that 8 became a 7.9999, what's going to happen? And why are we doing that? Because we are plugging in 4 from the positive side. This is 4. Again, the same principle. From the negative side, from the positive side. From the positive side will be 4.0001. Negative side, 3.9999. If you plug in from the positive side, because the question specifically asks for the plus sign right here, that means from the positive side, it'll be a 4.0001 that you're plugging in here. This x will become a 4.0001. So then what will become this outcome of after plugging it in? This number will become a 8.0001. Because this x is a little bit more than 4. And that's because the question specifically says it's a plus. If it's a minus, then it will be a 7.9999 here. And what's going to happen if you take away 8.001 from 8? It will be a positive number. 7.9999 minus 8 will be a negative number. And you always want to look at the overall of the expression. That expression is this one. That expression. If you plug things in and see that you have some sort of number on the top and the bottom, you have to look at the sign of the overall. So right now we have a minus 8 over 0. Minus 8 over 0. What kind of 0 is this? Because it was a plus on this side, and plugging in a plus 4, a little bit more than 4 into the x, we're doing 8.001 minus 8. That's a positive. So this 0 is technically positive from the positive side. So it will be a 0.00001 maybe. Again, these zeros actually exist. It's not perfectly 0. It's 0.001, 0.0002, whatever it is, whatever. If it was from the negative, if it was a 0 from the negative, it would have been negative 0.0001. Same concept, if it's a 0 coming from the left and the right, this will be a 0.0001 negative, this was 0.001 positive, and plugging it in, you will get here, it's a negative on the top, it was a positive on the bottom because our result was this one, not that one. Negative on positive is negative. That's it. Negative what? Negative infinity. So the answer is negative infinity. So again, whenever you see a constant over 0, the whole point is to plug in and look at what is the value on the top will never change. When you see a 0 on 0, the top is not the problem. The top is not a 0. It exists. It did nothing bad. That does not have a problem. The 0 has a problem because dividing anything by 0 does not exist. So yeah, that's just plugging in, looking for the sign of the 0. And vertical asymptotes is the same concept because C on 0 will happen, like I said, when there is an asymptote. It's going down or up. And by looking at your plus or minus infinity, you can see what the asymptote will look like. The function is tracing your asymptote to the top when it's a positive, and to the negative, then that's the negative infinity. We'll just use vertical asymptotes for mainly the curve sketching. Curve sketching is under chapter we're gonna be doing in Cal 1 for the second unit. But right now you don't really need to understand the vertical asymptotes for unit 1 at least, and that's another concept later for curve sketching. But basically, the function from right side and the left will not be the same, will not exist. It would exist as positive infinity if both are positive infinity, but usually we'd say there are profs that accept the answer as DNE for your limit. Let's say they're asking, this is 0, what is the limit as x approaches 0? It is positive infinity because both approaching from positive and negative will give a positive infinity as a limit, not in this kind of case where it goes to the positive infinity and then negative infinity. Then the limit definitely does not exist. But some teachers accept the answer positive infinity when they both go up or when they both go down. One more thing you have to know about limit is the sine and the cos function, what they look like. The sine function looks like this, and the cos function will look like this. And there will be problems where they are asking you what is, let's say, what is as x approaches 0 from the positive. No, actually, x approaches pi over 2 of x minus 1 over sine of x minus 1. So this is a perfect example where you have to look at the graph. You also need to know the graph of the sine and the cos function. You also need to understand the arctan, but that will be later on as well. This is a pi over 2. This is a pi. This is 2 pi. And same thing here. This is a pi. This is... oh no, sorry. That's a pi over 2. I totally messed up. That's a 2 pi right here. That's a pi and... oh wow, I realize I do not know my trigs. That's, yeah, so that's a quarter pi. That's a half a pi. That's another half pi, so 1, 2, 3, pi over 2. And somewhere here will be pi over 4. These are some stuff you have to know because not only that, you need to know that this is plus 1 and a minus 1. And plus 1 minus 1 will always be your best friend in your trigs, sines and cos. So this problem coming back, x approaches pi over 2. Well, first of all, if you plug it in, it's gonna give sine of pi over 2, which is, if you know your trig, that gives it 0. Oh no. Sine of pi over 2, why is it? Sine of pi over 2 is when the y value is, well, the sine is the y value of pi over 2 is 1, not 0, is 1, because, well, this is 2.5. pi over 2, and this is the cos, and this is the sine. And what's going to happen in the bottom is because it becomes a 1 minus 1 if you plug it in. So then that's again a 0 at the bottom. And we're not going to try to look at the timeline with the number line of 1. Is it going to be from the right or the left? We have to actually look at the graph instead of looking at, again, this is a c over 0, I forgot to mention. This is a c over 0 case again, from what we did over here. And this is now looking at 1 again. We want to know what that 1 is. If we want to know what the 0 is, but to find out what the 0 is, we need to know what the 1 is. What do you mean by what the 1 is? Is if the 1 is a 1.0001 or 0.000091 type 1. So this is a 1 from the negative. This is a 1 from the positive, right? Over here is positive, over here is negative. And whatever that 1 is supposed to be, either 1.0001 or 0.9999, your 0 here will end up plus or minus. How do you look at that? If you look carefully on the sine graph, approaching pi over 2, either way, from the negative or positive side, will be approaching 1 from the bottom. If you scan it from the bottom, going up, it's approaching 1, but will never be 1 because limit means x approach pi over 2. Approaching pi over 2 will never reach 1. So what does that tell us? It tells us that it's 0.999999 instead. So it is this case over here. If you do a, oh wow, that's gone. 0.9999, that is when it is approaching 1 from the other side. So this will be a negative. And negative 1, well, not negative 1, but 1 from the negative side, minus 1 is basically 0.9999 minus 1 will give a 0 from the negative side. So 0 was a minus sign on top. Pi over 2 minus 1 over 0 from the negative side. And that will give, because pi over 2 is like 3.14 divided by 2, that is more than 1. So the top is positive and the bottom is negative. The answer is negative infinity. So that's the type of c over 0 questions that we need to do. And that is basically it for the first quiz material. That is everything, absolutely everything you need to know. And jumping into quiz 2 material, we're going to be doing x approaching infinity or x approaching negative infinity. And that is when we do a 4 divided by 10, 4 divided by 100, 4 divided by 1,000, 4 divided by 1 million. What's going to happen? We did something similar before, but now is a very big number. Dividing it by a big number it will give you just a very, very small number. It becomes small. So what happens if I divide 4 by infinity? It will become very, 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 very small. And basically 0. Just 0. If it's 23 divided by infinity, that's 0. And the funny thing is, 23 divided by negative infinity also gives 0. Why? Because if you divide 23 by negative 1 zillion, that's approaching 0 from the negative side, yes. That's approaching like negative 0.00000001, but that's basically 0. Either way, approaching dividing by a negative or a positive infinity will always give 0. You do not need to care if it is positive or negative, or if the constant or is positive, if the constant is negative. It does not matter. The top and bottom does not matter. It will always give 0 because dividing anything by infinity is dividing by a very big number, regardless of the sign. The big number means the big magnitude, not the big sign-wise. So what happens when you divide by a very big number? Let's see a case like this one. And this is also one of my favorite concept in calculus. But we're going to divide each top and bottom with the highest power of denominator. That's a denominator. So here the highest power denominator is x to the 2. And you don't care about the power on the top. That's just the rule. Just follow the rule. So here x to the 2, x constant, the highest is x to the 2, divided by x to the 2, divided by x to the 2. Top and bottom, what's going to happen? Each value will be divided by x to the 2 on the top. Same goes for the bottom. And you will see that since we are approaching infinity for all of our x values, everything will become 0 if the top is smaller than the bottom. So 10 divided by infinity becomes 0. Like we said here. Remember how anything divided by a very big number, anything divided by a very big number is very small and becomes 0? Same concept here. 10 divided by infinity squared, that's 0. 8x divided by x squared is much bigger than x because it's the square of it. So this is a lot bigger than that one. Also becomes 0 because it's approaching infinity. This bottom is approaching infinity, and the top also plugs in infinity, but just do not care too much about how an infinity over infinity square is working. You do not need to know this. You just need to know when the bottom is bigger, it will bring it to 0. So it will bring it to 0 because the bottom is way bigger and it's approaching infinity. Here it's different. X squared and x squared, they're the same. They will cancel out, but 3 remains. So remember that the 3 remains here. Here, same thing. X squared cancel out, but 5 remains. This one does not remain, will become 0. This one does not remain either. What is the answer? You do not care about the limit anymore because you just did your cancellation. Your cancellation is a process of your work in this type of question when x approaches infinity. So that will just give 3 on 5. And what we did simply was to divide everything by x to the 2. Top and bottom. Now, what is so interesting about dividing top and bottom by the biggest power of the denominator is that it does not always work by simply dividing, because there is something called even roots. Even roots is a very, very tricky, but if you get it, it is a super simple concept. What am I trying to say? Is that when x approaches not infinity, but negative infinity. In a normal case like this, where there is no roots, and specifically no even roots, and I'm saying even because this case only applies for even roots. Let's say we do a normal limit as x approaches infinity question. Here, there is no roots. You do not see any even roots. Even roots means root 2, root 4, root 6. Not 3 cube root, not 5th root, 7th root. These do not apply, and I'll explain shortly. But let's say we do a normal limit x approaches infinity, but now this time negative infinity, because the tricky part comes when it is dividing by a negative infinity value. Dividing by negative infinity, if there's no even root, is doing the same process. So this will become a 0, this will become a 0. That one will cancel out, but 3 remains. Same thing cancel out, but 5 remains. This one becomes 0, this one becomes 0. Basically, anything divided by a big number, regardless of plus or minus, will give 0, remember? And that applies here as well. So it doesn't matter if the division over here was positive or negative, they will always do the same thing, just turns whatever that value was to 0. So then it's going to be a 3 on 5, once again. We did not care about any minus or plus infinity because there was no even roots. So now we're going to talk about what is even roots. Even roots, like I said, root of 2 basically is root of 4 or root of 6. This is the same thing. These are even roots, could be 8. Uneven roots were impair roots, I forgot. Odd roots. Odd roots, that's not odd, 5 or 7 or root 9. These are odd roots. Odd roots are fine with negative infinities because they're whatever inside, no, regardless of if it is positive or negative, they will always end up existing. For example, cube root of -8 is -2, and that exists because -2 times -2 times -2 becomes -8. But if you did a -4 root, that does not exist. That is D&E because root of a negative number just does not exist. And that applies for even 4. -4 fourth root of -4 does not exist. 6's root of -4 does not exist because what this is saying is that something times something times something times something 6 times will give a -4, and that is not possible because negative times negative, no matter how many times you multiply negative, if it is a pair number of negatives, if this is not a division, this means this guy is negative. If you multiply negative stuff, 2 negative stuff together, it will become positive. So even roots will always have to be positive inside, but the odd roots don't. What difference does this make? Well, that is when you cancel things out, or when you cancel things out by doing the limit as x approaches infinity definition, it will not work as simply dividing top and bottom by the same thing. That will no longer work if it is an even root. And let's just go by example. (3x minus 2 over 4x2 plus 20). What you have to do is divide top and bottom by the biggest power. The biggest power right now is actually x. It's a normal x. It's a simple x. Because x and x to 2 square is the same thing, right? Here, there's a root and there's a square, so it's divided by x to the square root. X square, root of x square. And this is divided by normal x. And this is actually wrong, because dividing the top with x is divided by a negative infinity. But dividing the bottom by x square root is infinity square root. That becomes a root of infinity. So this is a positive value where the top is a negative. Where if you just do it normally, if you do divide by x on the top, divide by x square root on the bottom, you're technically doing division by a positive number on the bottom and a negative number on the top, which is mathematically incorrect. What do you have to do? You have to add a minus sign on the top one. That's at least what our prof taught us, and I think that totally makes sense. Because now, if you do a negative, but the x is a negative, that will give a positive. That solves everything, because now the top is positive and the bottom is positive. Dividing. You're dividing top with positive, dividing negative by dividing the bottom by positive. You always do whatever to the top to the bottom. Whatever you do to the top, you do to the bottom. So now we can solve. X approaches minus infinity. You divide it by negative x. So it becomes negative 3, x on x, plus 2 divided by x. And here, it's always in the root. It's whatever is in the root stays in the root. But the root stuff does not have any sign difference, because there's nothing special about them. We added a negative here, but there's nothing added here. So there is no modification. And these will cancel out again because approaches 0. This is just a normal cancellation. It does not become 0. Minus 3 stays. This one becomes a 0 because the bottom is a lot bigger. The bottom is a lot bigger here, becomes 0. This one just cancels out, and 4 remains. But be careful, it's a root 4, not just a normal 4. So then we simplify, becomes minus 3 over 2. And that matters because these roots were even. But if it wasn't even, like I keep writing 6, like a 5 or like a 3, you do not need to care about these signs over here. You do not need to turn any of this x into a negative x. And that is because dividing by x to the 3, and if that x was negative, then the root of, well, the cube root, no, actually the normal root of x cubed is still negative. Whatever you have inside a cube stays with its own sign, because negative times negative times negative, well, these two become a positive, but then multiplying again will give a negative, and then positive times positive obviously will always give positive. So odd roots will always keep whatever the sign it had inside, even after the manipulation of the root, to the same sign. If it was a negative inside, it will give a negative as a result. If it was positive inside, it will give a positive as a result. And that is why the problem of dividing top and bottom with different signs does not occur. And obviously, if it was a limit as x approach positive infinity, you don't need to care about none of these sign changing. There's nothing to worry about. As soon as you see a plus, there's nothing to worry about signs in terms of dividing by an infinite number, so infinitely big number. Now we're reaching the squeeze theorem. And the squeeze theorem is really very simple, very easy. I think it's one of the most easiest concept in calculus. It's when you have 3 functions or more, usually 3. This is function 1, function 2, function 3. Let's say this is your function. Function 2 is your function. This one's your function. When a function, a of x, is squeezing f of x with b of x, like a sandwich. This is your bread, this is your cheese, and this is your bread. This is your sandwich. Whatever that's in the middle has to equal to the top and bottom because it is equal and smaller or equal and bigger than 2 conjoint functions, 2 functions that are very, very close or usually at the same spot as your function that you have. How does this help? It helps with mainly sine and cosine, actually, because sine and cosine, their functions are restricted to the value of 1 and minus 1, right? Either if it's a cos or a sine. Their waves are within 1 and minus 1 all the time for their y values. So what we can say about them is that they are within 1 cos of x or sine of x. And what's helpful here is that if you have a question, a limit question asking you something like x approaching infinity of x cos x over x to the square, you can actually simplify that to x over x. What we know is that x cos of infinity will always be, well, it's a wave like this. Cosine is a wave. It's not spiky like that. It's like a wave, right? So then it's always within minus 1 and 1, or 1 and minus 1. The y value is always within 1 and minus 1. So you know that top is either 1 or minus 1, like, or somewhere in between. But the bottom, you know that it is a very big number. What happens when cos of something divided by a very big number, well, inside is cos, dividing by also another, well, inside of a cos is a big number, and the division, the denominator is also a very big number. We can use the squeeze theorem to show our work that this actually becomes 0. The answer is 0. How do we show that? If you divide this by infinity or this by infinity, positive or minus does not matter. They will both give 0. This will give 0, that will also give 0. But then we're telling you the -1 sign is between -1 and +1. So by dividing -1 by infinity or 1 by infinity or sine of x by infinity or cosine of x by infinity, everything you can just divide by infinity. Because there's an equal sign here, we can say that the sign is in between 0 and 0. If something is in between 0 and 0, what is that something? Has to be smaller than 0 but bigger than 0. That's 0. So by the squeeze theorem, sine, or whatever this function is, as x approaches infinity, the answer is 0. To show your work in this kind of question, you just need to say by the squeeze theorem, answer is equal to 0. And squeeze theorem does not always have to be for cos or sine. It could be for normal looking function, but they will give you the function usually. Or you will have to figure out that it is a squeeze function by seeing a sine function that you can no longer simplify. Let's say this question right here was a cos x over x. Cos x over x, we do not know how to simplify any further. There is no cancellation. You can't cancel them. They're cosine, and it's not approaching 0 like a sine x over x has to be. So then you're gonna use the squeeze theorem, because if you plug in x with the infinity, when you don't find a simplification method, you always want to substitute, or you always want a direct substitution and plug it in to find the value. And here was -1 to 1. So if it is something like this, and they're telling you what is f of x, or the limit of f of x as x approaches, let's say 2, what you have to do is find the limit of that, and find the limit of that, and if they are the same, if they both give the same answer, then this one has to have the same limit. So the limit of this and the limit of this, if they're equal, this one has to have the same limit. Because in the graphically, let's say that's the first function, that's the second function, and this is our function, they have to end up coincide at the point x is equal to 2. That's what this theorem is telling us. This is the squeeze theorem. 2 functions that will coincide in the middle, our function that we're looking for. By finding the limit of this function and that function, well, if we can verify that they're the same, then the limit of our own function that we're looking for, whatever this is going to have the same limit. And these two, just do it with whatever methods that we already looked at. And now we're into logs and exponents. This is another review. I should have done at the beginning, but just remember that this is the exponent function, and that's your logarithmic function, or ln. We will use more ln than logs, actually. Realize that if you approach x to the infinity, the y is also approaching positive infinity. And if you approach negative infinity in your exponent function, it's approaching 0. The function is approaching 0. It's gonna touch 0. It does not touch, but it's approaching 0. And this idea is very important because there are gonna be questions such as x approaches infinity, e2 to the x plus 3, e to the x plus 7 over 3, a to the x minus 11, 11 e to the x minus 3. And you will want to again divide the top and bottom by now the highest power of e to the something. Right now e to the 2x is the highest in the denominator. Again, it's always in the denominator. Highest in the denominator is e to the x, so e to the x dividing top and bottom. And we're doing normal division top and bottom because this is a positive infinity. Yes, if it is approaching a negative infinity, there is another case. Again, negative infinity division is a little bit complicated, but don't worry, because e to the x or any exponent functions approaching negative infinity is very easy. The hint: if you approach negative infinity, what is the function approaching? It's approaching 0. Keep that in mind. We're gonna keep going with a normal positive infinity approach. Well, this one, everything's gonna be divided by e to the 2x. Same principle as when x was approaching infinity for x to the 2, x to the 3, whatever that was the biggest on the bottom, you divide that. Both bottom and top. So then, same principle. This cancels out, but leaves a 1. These two don't cancel out. That just turns into a 0. That just turns into a 0 because e to the x is very big, like we said. E to the x when x is infinity is very, very huge. So these both cancel out. Well, they become 0. They shrink to 0 because it's divided by a very big number, divided by a very big number. Again, divided by a very big number, divided by infinity. And here it's just cancellation, so 3 stays, because that was a e to the 2x divided by e to the 2x will cancel out and leaves 1. So the 3 stays. So now we have the answer 1/3. Okay. And the other case that I was talking about, approaching minus infinity, what's going to happen? It is a lot easier. And it is so easy that I really like it. It doesn't even matter what I'm writing. When x approaches negative infinity, e to the x function looks like this. X approaching negative infinity, the y value is approaching 0 because it's going down like this, and it goes down forever, approaching 0. So then all of these, you do not need to divide or divide by the biggest denominator. No, none of that. As soon as you see e's, as soon as you see these powers, and as soon as you see x approaching negative infinity, it's approaching 0. You just plug in. We finally spilled the amazing tea. We just need to plug in, that's all. Plugging in e to the 3x is e to the negative infinity, which is 0. Plus this one, also 0. Plus what happened was a 7. There's nothing was e to the x was a 7, so the 7 stays. 7 remains. 5 e to the 2x, x is infinity, e to the infinity is 0. Well, minus 0 again. And minus 3 stays, but it's a minus 3, careful. So now our constants stayed, whereas constants usually are the weakest over here. Dividing by a very huge number, 3 divided by e to the 2x, and the x is infinity, 3 divided by infinity basically is 0 miserably because 3 is very small. Whereas 11 e to the x was a bit bigger because e to the x is 2. An infinity, but it loses the bottom. The bottom is a lot bigger because it's e to the 2x. But here, it's a little bit the opposite, because if there is no e to the x here, there is nothing that multiplies 0 to it. So 7 stays, 3 stays. They are the dominants. They're the dominants, kind of. Dominating the answer. Equal to 7 over minus 3. Now, it would be really tempting for you to do none of these dividing by e to the 2x, and just straight to 7 over minus 3. You see this function, you go like, oh, I see 2 constants, probably just that. Or if it's like this one and you see a if you see this and you go like, oh, well, all of that will cancel out, and that will leave me with a 1 over 4. Don't assume this. Do not assume this, because if you don't actually do 1 by 1, sometimes you will miss something. It could have been a 3 to the 4x you just didn't see, and you'll be tricked, and this will no longer be right. The right answer will be 3 over 4. So do not skip your division step. Division step is really important. Don't just assume, oh, the biggest one, probably that's the biggest one, oh, it's probably going to be 3 over 4. Don't assume anything. These steps of division could be tempting to skip, but do not skip. It looks like, oh, it's obvious, it's just the constants. Do not do that. Just always do your classic individual step 1 by 1. So, recapping, e to the x, when x approaches positive infinity will go to infinity, so dividing by a positive infinity will go down to 0, but e to the x, as x approach negative infinity, the e to the x will approach 0, so multiplying something by 0 will become 0. So this one is about dividing by the huge number. Dividing by a huge number will cancel everything out, so lots of cancellation happen, like right here. But here, when the x approaches negative infinity, the value itself becomes 0. So it is just plugging and multiplying, which will result in 0. In two cases, they both deal with 0, but in different ways. This one, multiplying by 0, multiplying by 0. Whatever that didn't have an e to the x will stay. Over here, dividing by zeros, dividing by huge numbers, that becomes the answer becomes zeros, and whatever that was biggest and the most dominant, their coefficients will remain. Logarithm is not really concentrated, it's not really a big focus in the limit, but just remember that at 1, the ln of 1 is 0. At e, the ln of e is 1. Ln of e is always 1 because log of e is 1, and log of e means ln. Log of e basically means this e right here. Exponent to the 1 is equal to e, which is this e here. That's how log always work. So this equals to what? It's equal to 3. What we're doing really is 2 to the 3 is equal to 8. Same principle here. And log of e simplifies to ln. So we have ln, oh my god. We have ln of e, well, it's basically 1 because you're telling me e to the what is equal to e. Whatever that is, it's going to be 1. So with that idea in mind, we can do an example like, again, there is very little question of ln in limits, at least at Jack, that is. You divide top and bottom, again, with the highest power. And what happens is that, well, I kind of forgot to say this, but when you see a ln, always do the limit or the manipulation of inside and then do the ln. Do whatever that's inside, whatever work you have to do inside, forgetting that is a ln, and then do your ln stuff. So right now, if you divide everything by x to the 2, this is going to become a 0, that's going to become a 0, that's divided by a bigger number. This one will only cancel out. X to the 2 divided by x to the 2, 5 will remain. So that is going to be a 0 on 5. Because this one approaches 0, that one approaches 0, there's nothing on top. The top is 0. You have to realize that the top is 0. It's not 1. The top is not 1 here. It is 0. So 0 on 5 will be 0. Ln of 0, it is negative infinity. When x approaches 0, this is 0, the x approaches 0, the y approaches negative infinity. The answer is negative infinity. as x approaches infinity. This is a bit controversial. That is kind of true, because it looks like it's approaching infinity, and I was kind of bugged right now, but it looks like it's that way, but it really isn't, because when you plug them in, when you actually try to solve it, what you have to do is divide top and bottom. Whenever you see an infinity, you do top and bottom dividing by the biggest denominator power and canceling things out, whatever that's left, and ln of 0 just basically turns the observation of the graph into when the graph, I mean the lawn, approaches 0. So the answer is infinity. Another concept is the absolute value limits. We use a crowd to show whatever that's inside the limit, inside the absolute value. But inside of absolute value, whatever that cloud is, if the crowd is bigger than 0, then it stays a cloud. If the inside of the cloud is bigger than 0, but it becomes a negative cloud if the cloud is smaller than 0. That means if inside of an absolute value is positive, stays normal, stays positive. If the inside of absolute is negative, well, the function itself will now be a negative cloud, and you get rid of the absolute value. You don't want these signs. You don't want those signs to stay. Let's do an example. Limit as x approaches 3 from the negative side, and this is important because you will see that things become 0 and you don't want zeros. Basically, if you plug these in, actually the plugging in the absolute value is the very step you have to do. You have to direct substitute always in absolute value, and that's because you want to get rid of these bars. You want to get rid of these absolute value bars. And how to do that? It's to see if the inside is positive or negative. Positive or negative, as simple as that. If the inside is positive, you get rid of the bars, that's it. If the inside is negative, you get rid of the bar, and you also have to add a negative sign. So here, if you plug in normally, 4 minus 2 times 3 is a negative. What's going to happen? Well, this 4 minus 2x becomes a minus 4 plus 2x, or I should have done 4 minus 2x, and then you distribute the negatives. But either way, the entire function over here is going to become negative because the inside ended up negative when you plugged it in, and it was a 3 in our case. Same thing here, you just plug it in. But if you plug in normally, you realize that the bottom just gives 0. You plug it in normally right now. What you have to do is factor. It's very important to factor. Always factor, because now if you factor, you will see this one becomes x minus 3 and x minus 2. And when you plug in 3 here and plug in 3 here, obviously this will be a positive. But here, 3 minus 3 is a 0. How do you know if it is a positive or a negative? Well, we know that it's a negative. It is a 3 from the negative side. So this is 3. It's approaching 3 from the negative side, so it's 2.999999. You plug in 2.9999 instead of 3. 2.9999 minus 3 is negative. So now you know that the inside of this function, this absolute function, the inside content, is a negative. Because 2.9999 minus 3 is, 2.9999 is smaller than 3, so it will be a negative. Negative times positive will give a negative. So both top and bottom absolute values in this example became a negative. That is just the checking phase. What do you do now? We do a 2 minus. This, everything here will become a negative. And the bottom will also become negative, but the entire thing. And there's no more absolute value signs. This will become 2 plus 4 minus 2x and minus 2 to the x plus 5x minus 6. All I did was distribute this. This you can just minus and minus becomes a positive. Or you could have just distributed it, minus 4 plus 2x, and then another minus in the front, so it will become a 2 plus 4 minus 2x. And this one here, you can actually simplify even further. So it will become the bottom simplifies. X will become x minus 3 and x minus 2. Actually, you have to take out the 1 first. Minus 1 times x minus 3, x minus 2. And the top is x minus 3 times minus 2. Oh, no, not times. Minus 2, so x minus 3. Yep. So then now we can cancel out x minus 3's. That will give a minus 2 over minus 1 times, well, this one here is a 3 minus 2. You just need to plug it in. That is a 3 minus 2 here. So then here it will become a normal 1. And minus 2 or minus 1 will give 2. From here to here, it's just simplification. Minus 2, x plus 6. Why did I do a minus 2? Why is there a minus 2 in this one? Oh, yeah, that's why. Yeah, it was just factoring. So it was just GCF. Greatest common factor factoring, and that's a multiplication here. Sorry, that's a multiplication here. And that's pretty much it for absolute values, whatever that's inside. If it is a negative, then you add a minus in front of the function. If the inside is a positive, you just take away the absolute value signs, and you just need to keep going. If the inside of an absolute value is at 0, then you need to factor. Always factor. Or you need to know your trigs, but the trigs is, like I showed last time, if it is approaching a certain x value from the bottom, if it is approaching 1 from the top or from the bottom. Usually it's going to be from the bottom if it's a sign. It could be approaching 0 from the bottom. It could be approaching 0 from the bottom here. It could be approaching 0 from the top. Depends on where you are approaching from and what you're approaching to. So a piecewise function is, I think the last thing, no, there's continuity. So now there's the piecewise functions, which is when the function has multiple parts, x smaller than minus 1. There's 2 different functions for the range. And basically what you have to do is to find, well, it depends on the question, but the question will usually ask you where is it discontinuous, and what kind of discontinuity. There's 3 types of discontinuity. Removable discontinuity, where the limit is the same and exists means the same. The limit from the right and the limit from the left is the same, that means it exists, but the function does not exist, then that's removable. The function could be somewhere else or totally not exist. And another one is the jump discontinuity, where it is something from the left and another thing from the right. Again, it could exist or not. It could not exist, and the value could totally be another one. And the last one is the infinite discontinuity. And the infinite discontinuity when there is an asymptote. Goes infinitely positive, infinitely negative. Could both go infinitely positive, both go infinitely negative. It does not matter. As soon as there is an infinity, which is a vertical asymptotes, c on 0, constant on 0, dividing by a very big number. Sorry, not dividing by a very big number. Dividing by a very small number, or just dividing by 0, will give you a vertical asymptotes, and that's the same idea as the limit will become positive or negative infinity. That's when there is an infinite discontinuity. So an example like this, we have to first look at the discontinuities of -1. The question will ask you, for this piecewise function, where is the function discontinuous? So it could look like this. That could be the function. You never know what it looks like. I mean, you could kind of try to figure it out, but usually it will be very complicated ones like this where you can't really picture it. And you want to know, but you don't need to picture it in the entire course. You do not need to, that's actually the good part of calculus. You don't need to know any of the graph, and you don't need to imagine what the graph looks like. But this one has a limit from the left, this one has a limit from the right, and you have to make sure that you're looking at the right thing. Here is, let's say, -1. That does not make any sense here, but I don't know. Let's say that it is -1 right there. This is 0. And when you're approaching from the right side, you have to use the right side function, which is this one. If you're approaching from the negative side, you have to use the negative function to find the limit of this guy and this guy, and to see if they're equal to each other. If they are equal to each other, it will end up like this. This is the first function, this is another function, and from the left or from the right, they have the same value of limit. And plus that the function actually exists there, whatever that x is. If these two conditions are met, then there is no discontinuity, it is continuous. If any of these conditions are not met, then it is a discontinuity, and it will be either discontinuity, removable discontinuity, jump discontinuity, or infinite discontinuity. So I'll repeat, one limit has to be equal to each other, which actually teachers breaks down into 2 steps. A, limit from the left, B, limit from the right exists. They both exist, and that they are equal to each other. And another agreement, I don't know, I'm losing my vocabulary, is that the function actually exists. The function actually exists at that value. If all these 3 conditions are met, then the function is continuous. If any of this is not met, it is not continuous. And that is just simply by figuring out your limits here, your limits here, as x approaching from the negative, or x approaching from the positive because it's bigger, x approaching from negative because it's smaller here, and you do whatever your technique for finding the limit for each of them. It could be 1, 2, 3, never 4 I think, but up to 3 piecewise. So it could be like that. That's not really a function, but no, sorry. When there's 3, it's usually like this. They have different dots, and if there's a three piecewise function, it will become function number 1, function number 2, function number 3, and they're gonna ask for the overall discontinuity. So in this case, it's both a jump. If it's like this, this is a infinite discontinuity here at 2, and this one is a jump at 3. How to find that? Always, first thing, look for the limit. Look for the limit on the right, look for the limit on the left. If they're equal to each other, then you move to the next step of finding the actual function. Just plug in your x value into your function. So here, plug in -1 into the x, plug in -1 into the x. If it does not give 0 on 0, then it exists. Even if it's a 0 on a constant, that is 0, so that does exist. If it does not exist, or if it gives a different value, then it is discontinuous. What happens if the actual value is different from the limit? What does that mean? That means that whatever it is approaching is not the same as what the value actually is. That's the case here. When it's approaching 3, it is approaching 4. but the actual value at 3 is 2. That's also a definition of the limits. It's approaching something, but that something could be another value here. That's the value here over here. But what we care about limit is only what is approaching. It is approaching 4. That is the correct answer. But when you plug it in normally, when f of x, you plug in the x of 3, normally it will give another value from the limit. Then that does not exist. Well, in this case, either way it does not exist because the limit from the right and the limit from the left is not the same. So to recap, left limit, right limit has to be the same, has to equal to each other. If they are not equal to each other, that means it's a jump. Or if it's a c over 0 and the answer becomes a positive or negative infinity, that's an infinite discontinuity. And if they do both equal to each other, but the function does not exist or is different, then that's a removable. If it doesn't exist, it will look like this. If it does exist, but is not the same, then it's another value at when x is equal to 3. Either way, if function just does not exist, or function is different from the limit, then it is a removable discontinuity. And yeah, it's basically looking at when it is continuous and not continuous. As for the points to check means whatever limit x approach you have to do. Limit as x approaches something. That's something. What are we supposed to look at in all of these cases? The first is always the difference. Well, the differentiation number, I call it. It's from 0, from -1. If it's smaller than -1, it's this function. If it's bigger than -1, it's this function. So -1 definitely could be the discontinuity position. Other than that, where is it possible to look for if it is discontinuous or not is when the bottom is 0. You have to make sure that the bottom is definitely not 0, or the inside of a lawn is positive, or inside of a square root, even square root has to be positive. Those will come in, but most of the cases it's only about when the denominator is not 0. So then when the denominator is a non-zero. In this case, if you set everything to 0, the whole point of finding out if it exists or not is to just set the denominator equal to 0, find out what that x is. So in this case, x equals -4. So you should, for the x being -4, -4 means which function are we using? This function. We're using this function over here. So for this function, you find the limit. This function over here, find the limit as x approach -4. And for this function over here, it is x approaching when x is bigger than -1, so it does not apply. Same thing here. Look for the denominator. If the denominator is 0, then we need to find the x value when that is 0 equals to 0. So you're gonna look for x. Simplify. X to 2 equals to -1, minus x. And so x equals to -1. So you have to look for when x is equal to -1. Actually, is this also minus and positive 1? Where's my piece plus function? Yeah, so this case you should actually factor it out. Should have done otherwise. Yep, and then you set that equal to 0. So if you set that equal to 0, it's gonna be equal to. Oh well, this example does not work. Sorry, this example does not work at all. This was example that doesn't work. Either way, what we're supposed to do is we're given usually three functions that are piecewise, meaning it's jointing from this this value from infinity to this value to another value to positive infinity. There is going to be assigned functions that are different. We look for the discontinuity, meaning when the function itself does not exist, so when the denominator is 0, and where there is the connection between one function to another when the transition happens. And you will collect if they are discontinuous or continuous. If it's discontinuous, which type, when there are 3 types. And if it is continuous, then you have to just say that it is continuous at x equal to whatever that value is. Otherwise, piecewise defined functions, you can find better explanation probably than this one on Khan Academy. And continuity is another concept that we're gonna cover in calculus. And continuity basically is what we just looked at, but defined once again. So this is continuous, this is a jump, removable, and infinite. The continuity concept is that any polynomial, rational, radical, exponent, log, or trig functions are that the functions are continuous on their domains. They are all continuous on their domains. Meaning that if they don't have a denominator of 0, they are always existing on their domain. So domain means, for example, log. This is their domain. The domain will be from excluding 0 to positive infinity. Meaning the x value is from not 0, but whatever x value bigger than 0. And other ones, exponent, radical, rational, polynomial, they all exist on all of x's. So on R, all the R numbers. As long as it is not divided by 0. So that will usually happen if it is a fractional function, something over something. And as long as the bottom is not equal to 0, then it will exist. Yeah, inverse trig is one more concept that you have to know in the first test. So arcsine, arccos, arctan, and these are basically always set equal to 0. So if you set arcsine of theta, set equal to theta. Why did I say 0? Set equal to theta. Arcsine of x is equal to theta. X is equal to sine of theta, because when you bring arcsine to the other side, it will become a sine. So x equals to sine of theta. What is the theta? Usually the question will go like arcsine of half is equal to what? What you have to do is set that equal to theta. So sine of theta is equal to half. What angle would give a sine value of half? The domain of sine is this. It's just a rule. The domain of cosine, or arccos, I should say, is whatever within here. And the domain of tangent, or arctangent, I should say, whatever you find of a value is that. But here it is included, and this is not. This is tangent. And it will really make sense. I'll just show you what it means, really. By reversing from arcsine to sine, you find out sine of theta equals to half. What is the theta? Theta is when the sine of that theta is half. So sine is half, meaning the y value is half, is right here. So what is that? That is pi over 6. From remembering your trig. If it was instead cos of theta equals to half, you do the same thing but for the x value. So the x value is a half. What happens? Then that is going to be a pi over 3 instead. So theta equals to pi over 3. Here, theta equals to pi over 6. And if it is a tan, let's say arctan of root 3 is equal to theta. Is equal to what? Is equal to is the question. You set that equal to theta. 3 root 3 is equal to tangent of theta. So now we want to look for when tangent of theta is equal to root 3. Tangent of theta means sine of theta divided by cos of theta. And that is actually easy to find if you remember your trigs. This one is 3 and 2. So you divide the sine value by the cos value. And if you look carefully, this is pi over 3, right? Pi over 3, the sine value is root 3 divided by 2. That's divided by, which is multiplied by the opposite of the half that we have right here. The half. The opposite, because dividing is the same thing as multiplying by the opposite. We'll actually cancel out and give root 3. So this one here actually becomes theta is equal to root 3. And you will have to make sure that the tangent is within these values. Within these values. Always the actual radians, either pi over 3, pi over 6, or could be 11 pi over 6. You want to see within the domain of this arc, excluding the pi over 2 and 3 pi over 2, which is negative pi over 2. Whereas it is included in sine. In sine, it is included, these two dots. But in tangent, these are excluded when you transfer the arctan and look for the tangent. And another thing you have to keep in mind is, oh no, I forgot what I was trying to say. Yeah, so I remember now. When you have a value at the bottom here, under the x-axis, always use the negative pi over 6 or the negative pi over 3 or the negative pi over 4. Do not use 11 pi over 6 or like, what is this going to be? 7 pi over 7 pi over me, who said I know my trig, maybe don't know my trig. 7 pi over 4, yeah. So 7 pi over 4. Do not use these very big fractions. Always use the negative when it comes to arc sine, arc cos, arc tangent. And that is because they don't exist in these domains. They only exist as negative. And that is further because the opposite, the inverse functions look something like that kind of stuff. And if you look it up more closely, although you don't need to understand it graphically, they kind of look like a portion of something. And these portions of something only exists within this very short domain. So if you realize it is like a negative a bit of x values here and positive bit of x values here, negative here, positive here. So you always have to use the pi over 6, pi over 3, pi over 4 negative when talking about these guys here. Except for the cos, because cos, this one, these ones are actually positive. These ones you don't need to go like, I don't know, negative 7 pi over 4. No, you do not need to do that. These ones will be 2 pi over 3 as always, and 5 pi over 6 as always. You do not need to convert the cos one. It's just for the sine and tan. If there is any value under the x-axis, you have to make sure to answer them in negative pi over 6, negative pi over 3, or negative pi over 4. And I actually covered everything, so maybe one last trig. limit as x approaches negative of cos minus 1 3x to the 4 plus 8x plus 3 over 5 minus 2x to the 2. Always, whatever you do, plus 3. Whatever you do inside the function will become the cos, well, cos to the minus 1 is the same thing as arc cos of the inside limit. So you want to first evaluate the limit of the inside parentheses. So this one, since it's a limit as x approach infinity, I should write arc cos. Arc cos of inside, you divide top and bottom by the biggest denominator, which is x to 2, and this one is an even root. It's an even root, so we don't need to modify any signs. So if you divide that, it will become a root 3 plus 0 plus 0, because these will cancel out to zeros, divided by a very big number, and this will also cancel out to 0, but this one just cancels out the x to 2, and minus 2 stays. So then it will become limit as x approaches infinity of arc cos root 3 over 2 negative. And we do whatever we just did before, arc cos of root 3 over 2 equals theta, equals an angle. So root 3 over 2 equals to cos of an angle. When is the cos of an angle negative? Yeah, when is the cos of an angle negative x, negative root 3 over 2? Negative root 3 over 2, x is right here. So that value is 5 pi over 6. The answer is 5 pi over 6. And actually, you shouldn't really answer it by theta because the question itself was x. The question was using x as a variable. So you can show your work like this, but the actual result will be 5 pi over 6 is x equals to 5 pi over 6. Or you should just don't say x equals to, and that the limit as x approaches negative infinity is equal to 5 pi over 6. Usually the answer shouldn't need too much identification. And I lied, there's another thing that you have to know, it's the arctan. But the arctan is not just looking at circle. Sometimes you need to look at the arctan graph. And the arctan graph looks like this. Where the top and bottom is not 1 and minus 1, but rather pi over 2 and negative pi over 2. So same principle, x approaching, let's say 3 plus of arctan. They're going to mix in some few techniques. Inside, want to evaluate the limit inside first. Forget that there's an arctan, so that will be x minus 3, x plus 3, divided by factoring PSP will give x minus 3, x minus 3 as well. And that cancels out. You plug in the 3, which gives 3 plus 3 is 6 on top, divided by 0. But 3 is approached from the negative side, from the positive side. So this here will be a 3.0001 minus 3, which is positive. So this 0 is positive. So we have an arctan 3 over positive 0, which is positive infinity. Arctan of positive infinity, because if you remember, 6 divided by a very, 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 very small number will give a very, very, very big number. Dividing by a 0 gives a very big number. Dividing by a big number will give 0. It's the contrary, so it's quite easy to memorize. 6 divided by infinity will become 0, but 6 divided by 0 will become infinity. And that infinity is positive because this 0 is positive. If it was 6 divided by 0 negative, then it would have been a negative pi as an answer. Did I say pi? Negative infinity as an answer. But we're not done yet because arctan of infinity is not really a valid expression. But if you look at the graph, arctan as x approaches positive infinity is actually pi over 2. So the answer is pi over 2. If it was arctan of negative infinity, it is approaching, the y value is approaching negative pi over 2. So the answer will be negative pi over 2. And that is basically everything for the first unit. Some teachers teach the derivatives definition with the limits, which is when h approaches 0 of a function plus h, take away a function divided by x plus h, take away the x. This looks like a really confusing notation, which actually simplifies to plus h minus f of x divided by h, because minus x plus x minus x will just become 0. But this, you must be really familiar with this actually from Sec 3, from the third year of high school, third year of high school. You should have seen this. It's really this principle of, again, delta y over delta x is equal to the slope. And the slope is this red thing right here. But when it becomes really short, these deltas, when the delta become really small, it will practically look like that. And that's what we're talking about when that distance in between, which is h. So the h is like this distance right here. When the h is really small, what's gonna happen? That instantaneous slope, the slope here, will become so small between two dots that are so close that the distance is approaching 0. The distance between these two dots are so small that they're approaching 0. Now we're looking for the slope of that moment. How does that help? If the slope is not constant, if the slope, the change of the function, which is the slope, is not constant everywhere, and you want to know the slope right here when x is equal to 9. How to find that? Well, that is by using the derivatives. And derivatives is what we're going to be talking about in Unit 2. But in the first unit, what we can do about derivatives is by using limit. Because limit is when something approaches a number, but never becomes that exact number, right? But then it's approaching really close to something. So if you use the h approaching really close to 0, that means the distance of delta is becoming really small. And so the distance between the 2 points becomes so small that they're basically a dot. And that's what we want, because we want to know the slope at dot when it equals to 9, when x equals to 9. So the distance between a dot right here and a dot right here is so small that it's basically one dot, and we want to know the slope right there. So if you were to do the limit definition of derivatives, we use the function that we just saw right now. If you realize x plus h is not that scary, it's just x right here. That's x plus h, because this distance is h, and we want to minimize this distance, h approaching 0. But either way, if that h approaches 0, the slope that we want to know, that we want to find out, slope, because this is x and f of x, because f of x is y. This one is x plus h, and function of x plus h, which is the y. This is the y. That's also the y. But the y at when x equals to x, and the y when x equals to x plus h. So x plus h is what's gonna come into our limit definition. H approaches 0. So by taking it away, we're doing delta y, and we're doing delta x by doing just h, because if you realize the graph itself, the delta x is really just the h, because it's the length, the distance right here. And the top bottom, the vertical distance is the function when x is x plus h, take away the function, the y value, when x equals to x. The x, well, the independent value is just x. So then minus delta, well, delta y divided by delta x will give the instantaneous slope. Knowing all that, you can find instantaneous slope of any function using limits, definition of derivative. That's what it's called. You're gonna have x prime of x, f prime of x, which basically means the derivative, which basically means the slope. Whenever you see the f prime x, basically that's telling you the slope function of a function. If that was a function, the slope would have been that. If this was the function, the slope would have been that. If you look carefully, the slope is increasing. It's slowly increasing. The slope is like increasing. So is the slope function. And if the slope is the same, it's constant, then the slope function will look constant. Like this is just a straight line like that. And this one here, f prime, just means the slope function. So this is the f prime if that is f. If this is f, this is the f prime. So then now what we can do is to just change all the x's into x plus h and change all, that's it actually, and just keep the h. So this one will be f prime of x equals to 2. Change x into x plus h because it's x plus h, divided by, again, x turns into x plus h plus 3. That's this part. That's this part done. Take away normal f of x. Just copy the function divided by h because there's a h in the bottom. And what we do is simplify. We just simplify and use the limit as h approaches 0. First we gotta cross multiply so that they have the same denominator. Plus 3. Oh, actually take away. Times x plus h plus 3 divided by all of the denominator multiplied together. Times x plus 3. Actually, I could have just written as x plus h plus 3. And what you'll do is to distribute, and these as well. We're gonna distribute. Actually, the bottom you don't need to distribute. Sorry. Limits still h approaching 0. What's gonna happen is that you will basically end up with a very long expression. This one will become, if you distribute one by one without mistakes, that's what's gonna give you if you distribute everything on the top. And don't forget to distribute your negative sign as well, of course, because the negative sign comes with the 2x. And the bottom, well, the bottom, I mean, oh, sorry, the h actually stays. That's very important. The h stays. So the h can just bring it here on the left as 1 over h. And then the bottom, we'll keep it the same. And we're keeping it the same because the problem is always simplified on the top with this h, and the bottom h usually will turn into 0. It's not always the case, but most of the cases well, for me, I never had to touch the bottom. So just mind the top, as the top is whatever that was, and the bottom, well, it will just become the denominator. I actually never figure out why, but you never need to touch the bottom most of the case. There are cases where that will not work, so then you would have to touch the bottom. Right now we don't have to, and basically if you look carefully, it will cancel out. This cancel out, that cancel out, this also cancel out, and magic happens. There's only 6h left. 6h times 1 over h. H is also cancel out, and the bottom stays the same. But recall that limit as h approaches 0 is still there. H is approaching 0. Now that you canceled out your h, this is one of the h's you have to cancel out. You have to cancel this h at one point, which we just did with the 6h, because 6h is only the one remaining. And the last h that remains, there could be one or more h's remaining. You substitute that into 0. So that h will become a 0. The answer is 6 over x plus 3 times x plus 3, but then that's just x plus 3 squared. And something you should keep in mind is that h, there could be multiple h in your denominator. It could be a 3h to 2, could be a 3h, could be a 4h, and any of this will become 0. They will become 0 because h approaches 0. And the last step of after any simplification, like other limits, is to plug in your h. So plug in 0 into those h's, and if there was a constant before it, does not matter because 0 times anything will give it 0. And that's the final answer. So this video covered limits, every type of limits, every type of the functions that you will see, these rationalization, and all the tricks that you will need to know, the arctans, the absolute values, and infinity, so x approaching infinity, the square theorem, when x approaches infinity from negative side, positive side, and roots, even roots and odd roots. So slopes, x, sine x over x, fractions, limits of fractions, complex fraction radicals, like I said, and factoring. So factoring is definitely key to the first, especially the first, but all of calculus chapter in the first Cal 1 course.